So we're looking at a few things with electrochemistry. First is voltaic or galvanic cells, two names for the same thing, and the notation, the way we write those, and finding the potential for a voltaic cell. So this is one voltaic cell, and we see that we have these lines. We have a line here, double line here, and a line here. So when they write something like this, when you see this, the anode is always to the left, the cathode is always to the right. So remember, an ox and a red cat. The oxidation occurs at the anode. And this half cell is easy to understand because the anode is the thing being oxidized, right? And we have an ion in this half cell, and that ion is being reduced into the same metal that the cathode is made out of. So this one, it makes sense more than some others. So what we've got here is we've got a half cell and we've got another half cell, and they're separated. This indicates that they are separate, and there's a salt bridge. There's some way that ions can pass between them, but where they're not going to be mixed together. So so we have a reaction here. Magnesium turning into magnesium 2+, 2 electrons come off. This is our oxidation reaction. So if we find a list of reduction potentials, then we need to reverse it, and we reverse the sign. Chromium is being reduced. We see that, right? We see that this is not a spontaneous thing, but we've got magnesium, and its electrons have enough potential to do that. They will come off of the magnesium and go to the chromium because they'd be in a lower energy state there. So we have this potential for this cell. So separating the two half cells, and then what we can actually do is we can use this energy. So the electrons move from one to the other, and we put something in between those two half cells, and we can power that thing. Right? We can run the electrons through and make them do something. For a balanced equation, this one's pretty easy because there's only electrons and 2 chromium ions, 3 magnesium ions, etc. So one thing, we don't have the same number of electrons in these half reactions. That doesn't change the voltage. Okay, so leave that alone. Next, look at another one. We have another voltaic cell. This is using platinum electrodes. So this is still the anode, right? The cathode is still on the other side. But in this case, we have ions being turned into other ions, right? So still we have our oxidation over here. And the way it's written, we have a reactant and a product, a reactant and a product. So the iron 2 is going to be oxidized to iron 3, and the permanganate is going to be reduced to manganese 2. Some tables that you look at, look like this. I don't know if it's focusing, but they look like that. And you don't see a lot of reactions or half reactions. Let me show you this one. Maybe you can see that. Okay, maybe you can see all of these reactions at the bottom. So different tables will give you more information. Like the second table I showed you, this reaction is on there. So you couldn't, using the one on the old, on the AP test, it doesn't have it. But this is on a table that I'm looking at. So I just write the reaction. We've got a voltage of 1.512, a potential of 1.512. Iron turning into iron 3 is negative 0.767. You add them together, we do get a positive value. That has to be true for every voltaic or galvanic cell. They need to be spontaneous, and positive potentials are spontaneous. Right? If those electrons have this energy, they go. So we get a balanced equation, and when it's written out like this, it's pretty easy to see. We have 5 electrons here, we have 1 electron here, so just multiply this by 5. Again, don't do anything with the voltage, with the potential for that half reaction, just because you need 5 of these to go. This potential is per electron, so it's okay. Right, so those are some half reactions. So then what does this half reaction look like? So I think that's important to ask. And here, so I have the balanced equation written up here, and I have beaker 1 where the oxidation is taking place. On the right side I have where the reduction is taking place. So again, we got platinum anode, a platinum cathode, we have platinum electrodes here. We have like a voltmeter in between them to measure the potential between the two cells. And then we have a salt bridge to make sure that ions are flowing. So maybe this would be, let's say, KNO3. We got K plus and NO3 minus. And then we should be able to say which one goes where. Just a quick look, we've got Fe2 plus turning into Fe3 plus. There's going to be a positive charge building in this cell. So we should, since there's a positive charge that's building up, the nitrate should be migrating into that half cell. Whereas here, we have, this looks weird. We've got MnO4 minus turning into Mn2 plus. Looks weird. It's negative and it's positive. Why would a positive ion be moving into there? I'll have to look at that. This looks crazy. Oh, you know what else? You know what else? We've got the we've got H pluses. Right. So we've got a lot of H pluses going away. So we do. Since these are being used up, right? These are being neutralized. We have a lot of positive charges going away. So it's kind of those two. This would have to be in an acid, right? We need H plus in there. So since the H plus is going away, we need potassium to migrate into that half cell. All right, and then I wrote a form of Nernst equation up here. This one has ln. You sometimes see it with log and then some other numbers. So it could be either way. But this is a form of the Nernst equation. So I wrote a question. If we increasing the concentration of which ions should increase this voltage? Right? This is a voltaic cell. Electrons are going to flow from here to there. But if we wanted to increase the voltage, what could we do? Right? We have iron 2 and iron 3 in this beaker. What do we dump in? Right? If we have permanganate and manganese 2 in this beaker. What do we dump in if we want to increase the voltage? And then what do we dump in if we want to decrease the voltage, if you want it? And so I wrote here, if Q is greater than 1, so this is as it affects the Nernst equation. If standard values that we just looked up, the standard values assume a the standard values are for a concentration of 1 molar. Right? So standard potential, right? It's no matter what, Q is 1. Right? So anytime Q ends up being 1, then your potential is going to be equal to standard potential. Q, if we're going to calculate it, we would write product ions over reactant ions. So it would look like something like this. If Q is greater than 1, then ln of Q is going to be positive, and this term is also going to be positive. If that term is positive, then the potential would drop. So Q being positive causes the potential to drop. If Q is less than 1, ln Q is negative, and then this reverses and your potential goes up. So okay, if we want the voltage to increase, then we want Q to be less than 1, so we want the denominator. We've got to put in reactant, and that kind of makes sense, right? We want the voltage to increase, we've got to put reactants in there. So we put in either Fe2 plus or Mn permanganate. And if you want to decrease the voltage, dump in a bunch of product.